Good day, everyone. It is my pleasure to present our recent work on rebooting, research on detecting repackaged Android apps, literature review, and benchmark. My name is Li. I'm currently a DECRA Research Fellow at Monash University, Australia. This work is a joint work with Tegawendé, Bissyandé, and Jacques Klein from the University of Luxembourg. And the original paper has been presented at IEEE Transactions on Software Engineering. So before going to the details, let me first try to convince you why there is a need to conduct this work. As you can see from this figure, the total revenue of mobile ecosystem will reach 2.897 trillion US dollars in 2020, which is much larger than the GDP of many developed countries such as UK, Canada, and Australia. And this huge mobile ecosystem is mainly contributed by Android, as you can see in this figure. Android constantly occupies over 80% of market shares, being no doubt the most popular mobile platform in nowadays. And one reason contributing to such a success could be the number of available Android apps. As shown in this figure, there are over 3 million Android apps available on the official Google Play Store, and the total number is continuously increasing, except that there is a decrease at the end of 2018. By the way, if you are interested in understanding why there is a decrease, I strongly recommend you to read this paper. Anyway, the huge number of available apps do make Android one of the most popular mobile ecosystems in nowadays. But unfortunately, the big success of Android has also become the target of attackers. Where there is money, there are people who follow it, right? And in our work, we are interested in one of the most common types of attacks, which is named repackaging attack. So what is repackaging in Android? Let's assume that this guy represents a popular Android app, which is also known as the original app. And the packaging works by disassembling the original app and add some third-party payload to and then reassemble the app to make it a new app version, which is called repackaged apps. And in our context, the third-party payload can even be empty. The malicious people can just disassemble the original app and make some changes on the original code, such as to redirect the advertisement revenue from the original author to the attackers, and then reassemble the app to make a new version and so on to distribute. And this has been known a very common attack. And as early as 2012, our fellow researchers have started to characterize those repackaged smartphone applications. While until recently, April 2020, there's still existing a lot of repackaged apps. For example, there are like 11 malicious apps discovered where repackaged versions of a legitimate app called SM COVID-19. And this has been found by Symantec, who found like almost a dozen Android apps that pretended to be monitoring the COVID-19 outbreak. And actually, those repackaged apps kept many of the features of the original app, such as collecting location and device information for COVID-19 monitoring. However, the repackaged apps were also injected with metasploit, which allows for a reverse TCP connection and for various comments to be executed. And hope now I have convinced you that repackaging is indeed a serious attack in the mobile community. Despite that various research works have been proposed to tackle this issue, the problem still widely exists in our daily life, as shown in the previous example. Yet, it is not clear what is the status quo of repackaged app detection in our research community, right? So to fill this gap, we present to the community the first literature review and to understanding what are the current status of repackaged app detection. Well, by doing that, one of the major findings we observed from the existing work is that there are limited data sets made available for our fellow researchers to evaluate their approach or even to compare against each other. So that's why we further construct a benchmark to fulfill such purpose. So to summarize, the main contribution of our work is lies in two parts. One is the literature review, and another one is the benchmark. So now we will first briefly introduce our literature review. So the basic process of literature review is quite straightforward. So it started by identifying some research questions relevant to the topic we are interested in. And then based on the research questions identified, we're going to identify some keywords which will be used to search relevant papers. And after that, the step is we use the keywords to actually search those search papers from popular repositories such as IEEE, SM, Springer, and elsewhere, for example. And by doing the search, we need to also download the relevant papers. And expectedly, not all the papers will be relevant to our study. So we need to introduce some exclusion criteria to exclude some papers. For example, there are non-English ones or the short papers. And after that, in this work, we further did a backward snowballing process. So which is trying to, based on the funded papers, we read their released works, trying to find if they have mentioned some other papers which are relevant to our topic, but have not been included previously. So by doing that, we eventually collect all the papers and put them to the primary publication set. And then we do the data extraction, and the authors cross-check the results. And then eventually we write the literature review report. And in this work, the keywords we used in two groups. We make sure that at least one keyword in each group appears in the primary publication papers when we're doing the search. And the repositories we use these four ones. And we do apply some exclusion criteria, and we did a backward snowballing in this work. And based on this approach, we eventually identified 57 primary publications ranging from 2012 to 27. So when we first look at the distribution of the publication venues, and as you can see, until 2015, most of the papers are published at a security venue, while after that, more and more papers start to appear in our software engineering venue. And the number of papers we observe a peak at 2014, and afterwards the number is slightly decreasing. So that's why we named the title of the paper, we're trying to reboot the research. So because the packaged Android apps are still there, and we want that our fellow researchers to keep working on this, and so as to provide a promising approach to defend the repackaged apps efficiently and effectively, right? And then, based on the 57 primary publications, we by thoroughly examining them, we identified some challenges that are often mentioned by the authors. The first challenge is it's hard to meet market scale constraints. For example, in Google Play, there are over 3 million Android apps. How can their approach be efficiently in taking all the 3 million apps into account when detecting the packaged apps, right? And also our community is blocking a reference data set. That's why we did a benchmark in the end of this work. And also, it's kind of quite difficult to recognize the original app in a repackaging pair. So which one is the original one, which one is the maliciously repackaged one? It's hard to decide. And also, malicious authors may decide to apply some advanced obfuscation techniques to obfuscate their changes. And how can their approaches to efficiently and effectively deal with those obfuscation techniques? It's also challenging. And another challenge is to deal with the noises of common libraries. So because Android apps are written in Java, and there are thousands of libraries, Java libraries that could be used by Android apps. And those libraries could introduce noisy to when detecting repackaged apps, because those libraries could be very much similar to each other, and just like that. And another challenge is hard to constructing and exploiting a core dependency graph. This is mainly because Android apps heavily rely on events, and the sequence of the events can be totally different, depends on the execution environment. So when comparing the core graphs or how the events happened one before other, there is a need to properly taking those sequences into account when detecting if two apps behave the same or not. And also there are some corner cases and legal issues that need to take into account when detecting the packaged apps. So that's the main challenges we observed in this work. And after that, we also look at the taxonomies of approaches applied by our fellow researchers. And in our study, we find there are mainly 4 types of research. The first one is called the similarity comparison. Second one, symptom discovery. Third one, unsupervised learning. And the fourth one, long-term monitoring. Let's look at them one by one. For similarity comparison, the idea is very straightforward. They propose some tools, such as this one named Semidoid. Takes as input 200 APKs, and then disassemble those APKs, compare with their code at different level, like class, method, or APIs, or even the core graph, etc., and trying to identify the similar part and the dissimilar part. Eventually calculate a similarity score to decide if these 2 apps should be regarded as repackaged pair or not. And in our survey, we found that there are the state-of-the-art papers use different kinds of similarity calculation algorithms to calculate the similarity, such as the Jacques. The most famous one is the Jacques distance, and something also they use cosine, and even many of them introduced some customized similarity calculation algorithms. And that's the similarity comparison. So the second approach is symptom discovery. Symptom discovery builds on the intuitive assumption that the repackaging process leave marks on their repackaged apps. If such marks can be fully categorized, it is possible to spot the symptoms in apps directly, right? One of such examples is a tool proposed named Andro SOO, which tries to explore a novel and easily extractable attribute called string offset order, which it can be extracted from string identifiers listed in the bytecode of an APK. If such attribute is identified, and then we can confidently assume that this app is a repackaged one. Then there are another popular type is through machine learning, either supervised or unsupervised learning, which has been very popular nowadays. And the last part is through so-called runtime monitoring, representative approaches like include watermarking and birth marking. So the idea of this is more or less similar to what has been introduced in the image field. For example, given an image, the authors could add some watermark to embed the watermark to the original image and make it another watermarked image, which from the human point of view, it's exactly the same. We cannot distinguish the difference. In the Android APKs, it's the same. So the original authors could add some watermark to the original APK and make it a watermarked APK. And from the user's point of view, these two APKs should perform exactly the same. But somehow the authors have ways to check at runtime if this APK has been modified by others or not. So that's the main ideas of runtime monitoring. So that's the taxonomy of existing approaches. Then we look at the comparisons among approaches. And among the 57 papers we reviewed, there are actually only a small amount of approaches that's proposed to compare their approach with others. And as you can see, some of the tools even being as like the replicated private tools. So from this research, we find that there are many tools and datasets are not disclosed or made publicly available to the research community, so that it does not encourage innovation, since there is limited opportunities to reproduce, validate, and compare. And inspired by this finding, we actually go another step, trying to build a benchmark to the community. So the way we build the benchmark is quite straightforward. We first take a large set of Android apps from the Android root dataset, which contains over 10 million Android apps in nowadays. And we first try to extract the features from those APKs. And for each APK, we build a feature vector. And then we leverage unsupervised learning algorithm called EM to cluster those apps to different groups, to app clusters. And then for each app cluster, we try to pair those apps to make a likely similar apps, so that a pair of apps are from the same cluster. But in our manual investigation, we found that those apps, although from the same cluster, may not necessarily be the packaged ones. So eventually we introduce another step called similarity comparison. We compare those two pairs of apps to ensure that they are very similar to each other. So we put them into the repackaged repository. And eventually our repository named Repack contains 15,000 pairs of repackaged Android apps and has been made available on this GitHub page. And we leveraged the two existing tools to check those pairs of apps, and found that for Android and Semidroid, the similarity of these apps are very high. which shows that shows the reliability of our data set benchmark. And just as an example of repackaged app pairs, so these two apps are actually a pair identified by us. As you can see, they almost share the same skeleton, but just the content are different. So that's just one example of repackaged cases. So to summarize, in this work, we present a study contains a literature review for which we identified 57 primary publications up to 2017 related to repackaged Android app detection. And we summarized 8 challenges from those publications. And we identified 4 main types of approaches. And we found that there are limited availabilities of tool implementations and datasets in those 57 publications. And because of that, we further introduced to the community a Repack benchmark, which contains 15,000 pairs of repackaged Android apps, which we hope those datasets can be used to facilitate evaluation and comparison of existing and future repackaged app detection approaches. That's the talk I want. That's the talk I want to share. And with that, I would like to end this talk and invite you to give any comments and suggestions. Thank you very much.